Welcome to this lab class. In this lab class, we will see what is photolithography. We have seen in theory what is photolithography. We have seen that how the UV lithography works. We have touched upon how E-beam lithography works, right. You have seen mask, you have seen photoresist, all things in theory. Now, let me show you a video which is a process that we have carried out in the lab, in the clean room, and how we are using the photoresist spin coater in the lab environment. How you can use a photoresist, how can you spin coat the photoresist on a wafer, then how you can use different kind of mask. You remember we have learned in theory class the bright field mask and dark field mask. Same thing you will see here, how can you use the mask either bright field or dark field, and you can align the wafer onto the substrate, right. Then you will see the exposure. So, you will see the mask aligner which comes with a UV source, and you can align the mask by in x direction, in y direction and rotation, that is theta, right. So, 3 ways of aligning the mask onto the wafer. This is contact based lithography that we are going to show it to you in the lab. And finally, once you expose the photoresist, then how can you develop the photoresist so as to get the pattern that was there on the mask onto the wafer. So, this is what you should expect from this video, that what are the photolithography steps and how can we process a wafer. We will also see front to back lithography. What is that? I mean that if you pattern something on the front of the wafer and you want to create a diaphragm on the back side of the wafer, how you can do the front to back lithography, because silicon is opaque, right. So, we will also show it to you how the front to back lithography works. I hope you enjoy the lab session, and I will again come back at the end of the lab and we will see what you have learned from the lab video.
Hello everyone, greetings and welcome to this lab module on demonstration of lithography and cleaning process. So as you all know, and it will be covered in theoretical classes, that lithography is the heart of microfabrication process and mainly responsible to decide the final outcome or the final parameter which is known as pitch or resolution for a particular process. So in today's lab class, we will see lithography as well as cleaning of wafer, which is like an essential primary step for any process, and it can be repeated as and when required in the process flow. So as you know, in lithography, in the microfabrication pipeline starts with its thin film deposition, which can be done using PVD and CVD. So in PVD, as you know, it will be thermal evaporation, E-beam evaporation and sputtering. These are some of the options to deposit your final desired material with the desired thickness on the wafer. Whereas in CVD there are some other variants of CVD which you can use. Now at what particular, for which process and which material, which thin film deposition or additive technique needs to be used, that needs to be identified prior to sketching the process flow. Once your additive process is done and desired material is deposited on the wafer, the next step is to pattern that before etching. So that etching is a subtractive process, thin film deposition is an additive process. This lithography comes in between that in order to pattern that. Now the desired shape or desired pattern would have been already designed in a computational software which known as Clavin. Then what further you have identified the design will be loaded, and then light or UV light would be exposed through in between your wafer and your mask. So then whatever the pattern on mask will get successfully reflected on your wafer. So if I talk little bit in details about the lithography process, starts with cleaning and then further you are going to deposit your identified photoresist on the wafer. Now that photoresist will be put it on a wafer using a spin coating that depends on spin speed and spin time. For every PR, every photoresist, this time is identified, and if you see some of the data sheets of PR, you will get an optimized time that at this particular spin speed 3000, 4000, 5000, this much period of time you should coat this photoresist to get this desired layer. Once the photoresist is coated, you can you can directly expose the light in order to generate that different response, because as the name suggests, photoresist will act, or the chemical reaction happens in a different way where the light was presented and where light was absent. So accordingly your material or chemical reaction on photoresist will happen, which will be further used in a development process to obtain the final desired pattern. And once you have a desired pattern on your wafer, you can characterize it using the known techniques to identify whether the exact dimensions and pattern is generated or not. So this is like a overall flow of lithography process in microfabrication process. So today's lab module will quickly see the cleaning of wafer, followed by the patterning of PR on wafer, and then exposure, and whether we can develop the final pattern or not. So let's see.
So now we have the gold coated glass wafer here in DI water. Okay. So then first step of cleaning process in solvent is to clean it in acetone. So we have a petri dish, glass petri dish with acetone here. You can see the acetone bottle here. Okay. So let us leave it for 5 minutes here for cleaning in acetone. 5 minutes is over. So I am removing the sample from acetone and moving it to IPA here. Isopropyl alcohol. So let us leave this also for 5 minutes. So 5 minutes over. So I am removing the sample from IPA and moving into DA water. So now, basically acetone removes the contaminants. IPA makes sure the entire acetone is gone, and finally in DA water clean, the DA water actually removes the entire IPA, so that we will have the clean wafer. So now we have finally cleaned it in DA water here, right? And the next step is to blow dry the wafer using nitrogen. So we have a nitrogen gun here. So this step makes sure that the water is gone without leaving any marks when drying. Yeah, so the sample is clean now. So we will keep it for dehydration bake, which is a very crucial step before we spin coat photoresist. Okay, so it's very clean now. So the dehydration step requires heating the sample in a hot plate at around 110 degrees Celsius for around 10 minutes. Okay, so anything more than 100 degrees Celsius is good, but we typically go for 110 degrees Celsius. Okay, so let us keep it here for 10 minutes and then we will continue the process. So we are going for the dehydration bake. So you can see the hot plate maintained at 110 degrees Celsius. So let us wait for 10 minutes so that the entire moisture on the surface of the wafer is gone, so that we can prepare it for lithography step. So now we have loaded the sample for dehydration bake. So we will keep the sample, the wafer at around 110 degrees Celsius for around 10 minutes, so that the entire moisture on the surface of the wafer is gone. But while we wait for that, let us see how we do the process of lithography. And what we have here is one of the most critical equipments that's required for the process of lithography. It's known as a mask aligner. So the mask aligner that I am introducing today is a Midas MDA 400 M6 mask aligner, which is a manual mask aligner as such. Okay, and so we will go through the different aspects of this mask aligner now. Okay, so So why do we need a mask aligner, or why do we have different equipments like these, processes like this in the process of lithography? So when we think about it, the whole idea is to say create a pattern on the silicon wafer, okay, or glass wafer that we have. Now say in the sample that I have shown you, we have a glass wafer where we have coated gold in it, correct? So, and what we need, or what we are interested in, is to create patterns like these, what you see in this, a plate that you can see here, okay? And these are known as mask, photo mask. So you can see the patterns here, which we would like to have it on the wafer. So this is like a master pattern. So what is this thing? So a photo mask is like a master template, all right? So this is a master template of the pattern that we would like to have it on the wafer. So you can see something like a chocolate brown color shade in this area, right? And then there are a lot of patterns there. So these patterns, what you see here is called interdigitated electrodes that we are fabricating for a specific application in our lab. But otherwise, this is the dark area, which is actually chromium. And the transparent area is basically glass or soda lime glass. Now there can be different materials of photo masks, base materials, like it can be soda lime, it can be quartz glass, and so many different types. But what we have is a soda lime glass, and the opaque area is chromium. Now think about it that way. If we shine UV light from here, through the transparent areas the light will pass and reach the other side, while the chromium, which is the opaque area, will block the light. So basically now when we think about it, so if we have a wafer coated with photoresist, keep this mask on top of it like this and shine light, the pattern will be differentially, the light will pass through the pattern and will reach in a different way across the pattern, correct? So let us see how we use this mask in a while. Meanwhile, I would like to introduce you another mask as well. So in this mask, the majority of the area that you see within the circle, so this is a 5-inch photo mask. Okay, so this circle, the diameter of the circle that you see is 5 inch, and the majority of area that is within is actually transparent. While in this mask, it's the other way around, right? So the kind of patterns that we had here, that area is kind of transparent in this, and the rest of the area is all dark. So this is known as a dark field mask, and this is known as a bright field mask. Okay, so it's in a way you can say that the pattern of interest here is opaque, while here the pattern of interest is transparent, right? So this is a dark field mask, this is a bright field mask. So here on the top we have the UV light source. Okay, it's a chamber where the UV light source is kept, and in this machine we are using I line, which is 365 nanometer of UV. So the machine also actually can use deep UV, but we have now loaded a UV lamp that can produce I line or 365 nanometer. Okay, now the feature size that we can go or achieve has a lot to do with the UV light source that we use, but that's too detailed to go into. So now let's see a few components of this machine. So we have a lot of optics here, okay, which is like a microscope but with cameras and everything. Okay, we have the UV light source, and then we have a stage here, okay, and where we load the mask. So what you see here is like a plate, okay, in which we can load this kind of photo masks, okay, and then we have a chuck here, this one. This is where we will keep the wafer. So once the mask is kept here and the wafer is kept here, and when we close it like this and the UV shine from the top, then the UV light passes through the mask and reaches the wafer. So that's how the process is. But to just do this, I mean, just to keep the mask and wafer and shine UV light, why do we have a lot of complexity like this? So the idea is, many a times in microfabrication processes, we will have multiple stacks of materials, right, which are patterned, which are to be patterned. So we will not be just using one mask, probably we will be using 5 masks, 10 masks, and so on. And especially for microelectronic fabrication, people use 20 masks, 30 masks. It goes a lot, right? So in our case, if we need multiple masks and the patterns are all too small, right? So in this machine, we can go up to around 3 micrometers of feature sizes. And when we talk about 3 micron, there is a lot of ambient vibration that can actually creep in, right? So this machine is actually suspended in the air, okay, right? So this is suspended in the air so that the ambient vibrations will not be there. And also the idea of this using this machine is that if we have a pattern that is already transformed over a wafer and we have a second mask which is used to create a pattern on top of this pattern, we need to make sure that this can be aligned properly. So this alignment step actually, for this alignment step we need this machine, and I will show you how that is done here. Okay, so the dehydration bake is complete, so I'm removing the wafer. Okay, so we have the wafer now dehydrated. So the next step is to do spin coating. We will see how to do the spin coating process. So we have here a spin coater. Okay, this is the tool that we use to load the wafer, pour photoresist, spin at very high speed. So we will see how we use the equipment. So I'm opening the spin coater lid, placing the wafer on the chuck that we see here. So it's a vacuum chuck. So once we place the wafer and switch on the vacuum, the wafer will not be able to move, which is very important because we are rotating at around 4000 rpm, and if we don't hold it properly, the wafer will fly out. So then we select the recipe. So we have already a recipe set which is to based on the data sheet that we have for the photoresist. We have to spin coat the photoresist at around 4000 rpm for around 40 seconds, and since we are using the 3012 photoresist, positive photoresist, we will have to rotate at 4000 rpm for 40 seconds so that we will get a thickness of around 1.2 microns. So you have the wafer here. Then we have the option to switch on the vacuum. You can hear a humming sound, right? So now if I try to move the wafer, it will not move. That's because the vacuum has held the wafer properly. So the next step is to add the photoresist, which we have it here. So the photoresist is something like a brown liquid. Okay. Now I am using a dropper to take the photoresist. And you can see here the photoresist getting covered on the wafer, right? So we have covered the wafer with the photoresist now. The next step is to spin coat the photoresist, right? So yeah, so we will see how we spin coat it. So I'm closing the lid. Okay, so the vacuum is already on. Then what we have to do is press start, and you can see inside it's a bit foggy, but you should be able to see through inside of this glass lid how the wafer starts rotating, and the excess photoresist will fly away due to the centrifugal force, and very thin layer will be there. So it's a 40 to 60 around 60-second process. So now you will see the excess photoresist have flown away, and you can see that slowly the speed will increase to 4000 rpm. So the the physics behind spin coating is very interesting. So you can always go and read some extra materials on the same. It will be really fun to see how viscosity, temperature, humidity, so many different factors actually affects how we can get very uniform thickness across the wafer. And the thickness of photoresist is a very critical parameter when it comes to photolithography process, which we will be seeing in the next step, right? So getting very uniform photoresist from center of the wafer to the edge of the wafer is very critical. And as per the data sheet, when we spin coat this specific photoresist at the RPM that they have suggested, we get around 95% uniformity across the wafer. So now the spin coating process is done, and if you might be able to see a very thin rainbowish kind of tint on the wafer, okay, which was, I mean, previously it was pure gold, and now you might be able to see a rainbow kind of shade. So that is created by the photoresist that we have spin coated. Now we will take the wafer from here, and we will shift it to pre-exposure bake in the hot plate. Okay, we will do that process now. So I'm switching off the vacuum and taking the sample out. Okay, and we will slowly shift it to the hot plate, so which is maintained at 110 degrees Celsius. Okay, and we have to keep it here for 60 seconds. So this step is very crucial in the way that the excess solvent that is there in the photoresist gets evaporated, and then all we have will be the photosensitive material and the cross-linking polymer that will be available in the photoresist. So we will keep it here for 60 seconds, and then we will go for the next step. So I have taken the sample out of the hot plate after 1 minute. Okay, so now let's go for the lithography process here using the mask aligner equipment. So now I'm going to load the wafer. So as I have explained earlier, we have a mask holder here. So first we will have to open the mask holder. So now I have opened it. So the next step is to load the wafer onto the chuck that's here. So this is again a vacuum chuck like what we have in the spin coater. So I have placed the wafer central in the chuck. Okay, and to prevent the wafer from moving around, I'm switching on the sample vacuum. So now the wafer cannot move, it's sitting stable there. So the next step is to load the mask. So I'm opening the photo mask that I showed you earlier. So as I said earlier, this is a bright field mask, and if you think about it, the pattern is on the dark side, right, or the chocolate brown side, which has chromium in it. So, and the light comes from the top. So we need to make sure that this pattern side or the brown side has to face the wafer. So I will be loading the mask like this onto the mask holder. Okay, and once I load the mask, I press this button here so that the mask vacuum will be on and the mask cannot move further. Then the next step is to close this mask holder so that we have the mask on top of the wafer. Okay, now we will go for the alignment step so that you can see what's going on in the display here. See, now what you see here is the machine came forward, correct? So that we have the optics now aligned on top of the mask, and you can see on the left hand side and right hand side two different images, right? And I'm just adjusting a few of the the micro manipulators here so that you can see how the image changes. So basically the micro manipulator or the microscope that is controlled with this micro manipulator, okay, is actually viewing the mask, and you can see different patterns. So I am adjusting the zoom so that you can see different patterns that are available in the mask. So see, these are all different patterns. You can zoom it and you can see that I told you that this is a interdigitated electrode. Okay, I'm adjusting the illumination a bit, but it's still blurry, so I am adjusting the focus, and now you can very clearly see finger kind of structures which are known as the interdigitated electrode. On the other hand side also you can look at it. So basically we have two microscopes with cameras so that we can do the alignment, and what you see here is the alignment marks. Okay, these are also very essential. Okay, you can see different patterns. As I said earlier again during the previous explanation, that if we have multiple masks, we need to make sure they are aligned well. So we use different patterns like this. See, these are all like verniers that we have provided on the mask design so that we can align very well. Okay, so these are all different patterns. Now I'm just zooming out a bit so that you can, and I'm adjusting the illumination. Okay, so now do you see a shadow there? a shadow being formed under the pattern. So that's basically the wafer that you have. So the shadow of the pattern is actually falling on the wafer. So when I move it up, move the wafer up, you will see less and less shadow. And when the wafer touches the mask, the shadow will be completely gone. And in the process that we are trying to do, okay, we are going to do a proximal lithography. Okay, so we first touch the wafer and the mask so that they align completely. Then we do something known as a wedge lock, okay, so that it will remain there. And then we move down the wafer by around 50 microns. Okay, once that's done, there is a small separation between the mask and the wafer, and then we can go for the exposure step. That's the next step. So next step is the exposure step. So I'm going to the exposure mode here. So you will see that the equipment will move forward. Okay, so now the machine has moved forward into the exposure mode. Okay. Now before exposure, what you can see here in this calculator here, so if we press the shutter button, exposure will start. Before that, you can set the time of exposure that you want, and this corresponds or directly proportional to the dosage that we need. Okay, so the dosage is the amount of UV energy that we have to provide to the photoresist so that the pattern of interest will be developed, okay, or pattern will happen, and that's available on the data sheet. And for our equipment, we have to calibrate how much UV energy is there. So based on that, we have to apply around 4.5 seconds of UV so that we will get the pattern developed. So I have set it to be 4.5 seconds here. And then I am going to press the shutter button. And then you can see the UV light actually coming and shining on the mask and wafer. See, around 4.5 seconds you can see the UV light. And after the process, the machine will go back and the process is complete. So now that the exposure is done, I am removing the mask holder lock so that I can open the mask. And then I am going to remove the sample vacuum so that I can remove the sample from the chuck. So now the exposure is complete, and the next step is to do the post exposure bake, okay, so that we can develop the wafer later. So we will again go back to the hot plate. The hot plate is again maintained at 110 degrees Celsius, and we have to do the bake for around 60 seconds again. Okay. So I'm loading it. So now I'm removing the sample from the hot plate. 60 seconds is done. And next step is to do the development process. Okay. We will do the development now. So I'm just placing the wafer in water for now, DA water here. And I'm adding the developer solution. So the developer reacts with the photoresist and removes, since we are using a positive photoresist, it will remove the exposed area of the photoresist. And this typically takes around 20 seconds of time. Okay. So I'm moving the wafer here from DA water to the developer, and you can see some color changes that will happen. So that is the excess photoresist being stripped off. This process will take around 20 seconds. Okay. So I'm just taking out the sample and see if the exposure development has been complete, and I'm shifting it to DA water. So yeah, the development process is complete. Okay, so I will show it to you. So what is, you can see the patterns that has developed properly on gold. Okay, so this is how the lithography step works, and you can very clearly see the thing. Now the next step is to the dry the sample, and then we can go for the subsequent etching step, or that's the next step.
I hope you like the video, and now in this video what you have seen first of course how to use the photolithography, that is yellow room. You have seen that the reason of yellow room is to avoid the UV exposure, right, because you know that photoresist is a photosensitive resist, that is why it is called photoresist. So, it will get exposed in the UV light, in this white light. So, we have to have a yellow room. Yellow room avoids the UV or white light, and then you have seen, what you have seen, how can we use the photoresist and how can we coat the photoresist at different spin rate. So, first you need to coat the photoresist at a 500 rpm, around that value, so that you have a uniform coating, followed by changing the rotations per minute. So, if you go for 1000 to 2000 to 3000 rotations, the photoresist will get thinner. If you increase the time, photoresist will get thinner. If you decrease the time, photoresist will get thicker, right. If you reduce the rpm, photoresist will get thicker. So, the role of the spin coater and photoresist is what you have seen through this video. You have also seen how can we perform the soft bake, and then how we can align the wafer with the mask, how we can expose it, you can unload the mask, take the wafer, develop the wafer in photoresist, and then you can inspect. So, once you develop the wafer, what you do? Once you develop the wafer, that means you have to dip the wafer in developer, take it out, then you rinse it with DI water, right, and then when you dry it with nitrogen and you inspect the patterns that are there on the wafer, right. That is our photolithography. So, I hope that you like this video, you understood what exactly photolithography means and how can not we do just not front alignment, but how can we also do front to back alignment, right. We do not have to just focus on front alignment, but also front to back. This is very important when you talk about MEMS. If you just talk about sensors in general, then those sensors would not have a diaphragm for micromachining, then in that kind of case, or a rotational things like gears, micro gears, then you do not call that as MEMS, right, and that we have already seen in the first lecture, if you recall, that what are MEMS. So, this particular photolithography can be used for sensors and can also be used for MEMS based devices that include sensors and includes transducers, because for transducers also sometimes you have to go for a diaphragm. For sensors also sometimes you need to make a diaphragm, and then the lithography step remains almost same, except how to perform front to back alignment. So, I hope that you like the video, and I will see you in the next lab video.